What year was that when you got into printed circuit card fabrication?
um, 3/4 through 1970.
So at that time, you said initially it, seemed very complex. Has it changed much?
Well, unfortunately, um, 53 years later, we still make printed circuit boards the same way.
Hello, everyone, and welcome to the Altium On Track podcast. I'm your host, Zach Peterson. Today, we're talking with a legend in the PCB industry. His name is Happy Holden. You've probably seen his name grace the author position on many articles in the blog. He has a wealth of knowledge about the history of the industry and especially advanced fabrication techniques like HDI. And I'm very excited to talk to him today, and I hope you're all very excited to listen to this very knowledgeable guest. Happy, thank you so much for joining us today.
Good to be here, Zach.
Yes, it's great that we actually get to talk to each other on camera in person. I know we've talked at least once in the past in a different context, but I'm excited to talk to you today about several different topics. But I think now would be a good time to maybe give us a brief overview of your career and how kind of the industry has progressed alongside your career.
Well, yeah, in the last 53 years, um, I was a chemical engineering major at the university, but also stayed on to get an advanced degree in control theory. Although I enjoyed chemical engineering, I really fell in love with the whole computer control process part of chemical engineering, and decided then to build on that love. Since my university um, very early emphasized a lot on writing software and simulations and actually hands-on control of chemical processes and the sensors therein. So, and because of that, I was actually recruited by Hewlett Packard. Um, they were looking for a chemical engineer with a bias towards electronics, and my major professor had recommended me because I was really not aware too much of Hewlett Packard from the university level. Being in Oregon, all of our electrical laboratories had the latest state-of-the-art Tektronix equipment, and if you got to lab late, you ended up with these old HP 150 oscilloscopes that would never trigger properly. So that was the only introduction I had with kind of war surplus HP scopes rather than the latest and greatest Tektronix, which is headquartered there in Oregon. But in Hewlett Packard, it was quite a departure since, I had mainly looking at Dow Chemical and DuPont and chemical companies as a career, and being introduced to Hewlett Packard and electronics was quite a departure. But being relatively young, Hewlett Packard was a small but growing company, just 2,000 employees, 200 million in sales, but was, being Silicon Valley, totally different from, 100-year-old DuPont and something like that, where I stayed at the DuPont um, hotel and ate in the executive dining room, and they talked about how they had planned out my next 30-year career in DuPont with all the other chemical engineers. Um,
You
and
don't really see that anymore.
No, but back in 1969, where it's Hewlett Packard was totally different, and fortunate because of the various influences, I already had an extensive background in computer programming, but also designing computer interfaces since I worked as a technician at $2 an hour for the university, and also did oil exploration with shell oil and paleomagnetic work in the oceans off of the coast of Oregon. And so, back in 1970, that was really quite a thing. In fact, Hewlett Packard was surprised that I had so much experience with computers, since they said that, typically they don't see this much computer experience unless you're a graduate student. And I said, no, the emphasis here, we started at our freshman year with learning Fortran, and then our sophomore year with writing simulation software for things like that. And so we constantly were heavy on that, maybe because of the influence of Tektronix and other electronics companies coming up. But so I spent 28 years at Hewlett Packard in many different roles, 14 different product divisions, including time in Finland working for Hewlett Packard, and then time in Taiwan working for Hewlett Packard doing application engineering, and HP having me start a printed circuit manufacturing operations there.
So just to jump in on that, your career is long enough that it kind of spans this time period where I think a lot of companies were starting to look overseas for solutions to their fabrication needs. Is that correct? Or was Hewlett really a driver of this?
Well, I don't know too much, but in the 1970s, the majority of printed circuits in North America were made by the OEMs. Only 5% were of the whole capacity was what we call merchant makers. 95%. IBM had their PC shops. We had 7 printed circuit facilities around the world. Texas Instruments, Western Electric had these monstrous PC shops. Automatic Electric, the telephone companies, and so it was very much one of what we call captive. In other words, we made just for our own product line, and the IPC was just starting out, basically also because of the OEMs, like Philco Ford and things like that, getting into electronics. The IPC was just starting up. But over that time, unlike many other companies, Hewlett Packard kind of was always global. Over 55% of HP's revenue were derived from outside the United States. And so we already in the 70s had operations in the UK, manufacturing in Germany, manufacturing outside of Tokyo, and we're highly diversified. But what was happening as HP grew was fortunate that our focus on computers started out in the right tack. Our computers were initially focused on being instrument controllers. That is a way to automate all the voltmeters and counters that we had, especially to build custom test systems and things like that. And so our architecture was very much real-time interrupt driven, rather than being like an IBM mainframe where it was computational. Because we were going to control instruments, and these things, dozens and millions of them, when they've made a measurement and they generate an interrupt, they want to be serviced so they can continue on working. So fortunately, that happened to be a winning architecture for computers compared to everybody else. And in time led us to timeshare, because people that were buying our computers, we found out weren't controlling instruments with them. They were using multiple terminals and multiple printers. And because we were interrupt driven, it was relatively easy to put together a timeshare system where you could service 40 or 50 or 100 users simultaneously. And because of that, we started changing our design and actually came up with an improved architecture for business use of computers. Eventually, we would have three different mainstreams of computers: scientific calculation for CAD, instrument, real-time, manufacturing-driven, and then business-oriented kind of computers. And so making printed circuit boards for those things, they were highly, highly different in what each group required. And so at one point, I think in the 80s, we had 25,000 different products, 25,000 separate different electronic, with each product having 3 to 10 electronic variations on them. And so printed circuits were really, really all over the map in terms of technology, which was great. Now, I started, though, in semiconductor substrates. That I was recruited into the IC substrate making business in order to do what we called the silicon on sapphire. In other words, we built our gigahertz-based components on an epitaxially grown sapphire. And then we would sputter it, metallize it, and produce circuits like that. And it was only 6 months later that HP asked if I would go down the hill and help out the operation making printed circuit cards, which I had some familiarity with, but didn't know a lot about printed circuit manufacturing. And then walked into that manufacturing operation, was totally surprised at how these things were being made. I mean, it seemed like the most complex manufacturing process I'd ever seen. You got machine tools and testers and image transfer, and then all these wet chemical processes and environmental aspects, so it was an engineering delight. Unfortunately, they had a lot of problems, which I was down there to help them solve.
If I could just jump in real quick, what year was that when you got into printed circuit card fabrication?
3/4 through 1970.
So at that time, you said initially it seemed very complex. Has it changed much?
Well, unfortunately, 53 years later, we still make printed circuit boards the same way. We've evolved it, but we fundamentally haven't changed the process that I was introduced to in 1970, which
Sure.
is one of our issues, is that today we're dealing with state-of-the-art technology that we inherit from semiconductors, but we're still manufacturing with a process that was used in 1970 or 1968. We don't ever seem to obsolete anything. We just keep adding to it, and it keeps getting kind of more complex and more options available. But nothing ever seems to kind of go away. And the materials are a lot better today.
I've heard people make the same remark about CAD tools, that some of the older CAD systems that started like in the 80s, they didn't really evolve. They just kind of Band-Aid on top of them over and over again, and then they morph into what they are today.
Yes, one of the dilemmas of CAD tools are you have libraries, and for each one of your printed circuit cards, and if there's a lengthy life, and military products have to be supported for at least 15 years, but many products have a life longer than that. You have this history of all of these libraries and databases, and so you're kind of trapped into saying that to completely start over with a state-of-the-art CAD tool that has a different databases, starting from scratch. And then what do you do you got to support two different systems. You've got to support the older stuff. So there's a tyranny in CAD tools, based on that library. It's always been a part of our history, and unfortunately, like I said, in HP, being in printed circuit manufacturing, I would complain about the quality of the designs I was receiving that had to build. And the HP vice president said, well, since you obviously seem to understand the problems, I'm going to promote you to be head of design for the group. And I said, no, I don't want that job. He said, no, you've got the job now. But, and one of the first things I did, was review our design tools, and did the thing that nobody else had the nerve to do. I said, we're going to use a different design tool, because the one we've just benchmarked, it's 5th out of 5. We're going to start employing number 1. Now, we did it kind of in the back room. We kept everything in the front room that management saw the same, but all the hard work was being done by a different computer on a different set of software in the back room. But eventually Hewlett Packard bought those companies, and so we could take down the wall, because we were actually using HP products now, and not someone else's. But yeah, I go all the way back to when we were hand taping things with this red tape at 4x speed, and then would photograph it on a big, huge camera, and really enjoyed our first computerized calibration digitizing system from Gerber Scientific that allowed us to start to go into the digital age in terms of printed circuit design from the kind of pure tape method. But
so when they call it image transfer, like you were literally doing image transfer.
Oh yes, and we experimented with a lot of innovative techniques out of Europe, where we could actually draw the circuits with felt tip pens, and then modify the camera to shoot it 4 times, which then cleaned up all of the wobbly lines into something orthogonal called DigiRaster. But then as CAD tools took over, especially CAD tools, also, they were basically mainframe based ones, but as they started to get down into using the mini computers like we were manufacturing, we could use our own computers, and just had to buy the software and things like that but that also was one reason why we morphed into an architecture that was scientific, calculation based, because they require much greater resolution than, say, a business machine and things like that, which is unlike most companies. We had 3 or 4 totally different architectures. And strangely enough, people don't know this, but our handheld calculators were actually the same architecture as our computer. And the calculators were created using a high-level language that we compiled down into to become this, handheld device, but was actually shared architectures with our computer brothers. So I was in HP for 28 years and got trapped in one of the rules that they came up later. As HP was vertically integrated, we actually manufactured everything that went into our products, which gave us a competitive edge, including the semiconductors. HP was always one of the most advanced in Silicon Valley when it came to semiconductor production, partially because we were making microwave devices, from the end of the war, and things like that, which, and that's where I got involved with is thin film circuits for radars and things like that, not on circuit boards, but on sapphire substrates, because they were even in 1970, operating in the gigahertz, even in 1970. I think the highest we ever got was about 300 gigahertz type products, which today sounds fantastic, but we're talking about 53 years ago, not today. And consequently, I actually made circuit boards that were not electronic, but photonic, because we got into photonic for the optical industry, measuring test equipment, and the circuitry was actually photonic based with waveguides rather than polymer waveguides rather than copper circuits, things like that.
That's interesting you bring up photonics because in one of the older newsletters that Altium sent out, we had a little news headline that was a research paper that had just recently come out that was doing exactly that, which is polymer waveguides on organic substrates for printed circuit applications. Exactly what you were doing.
Yeah, and in fact, my Tech Talk column in March for the PCB 007 is a shortened down version of a Tech Talk about integrated polymer waveguides in printed circuit multilayers. A little about that from much larger articles I've written and kept up with. But that technology for me goes back to 1998 when we were actually making photonic printed circuit boards, which even today people are still talking about. But we were doing it because we were running laser signals all over the circuit boards, and whereas copper wire or trace, you can multiplex a signal on a waveguide. We can multiplex each laser wavelength and run 100 of them down the same waveguide without crosstalk. So in many ways, photonic connectivity is 100, 1,000 times more capable than electronic communication. Plus, we don't have any signal integrity issues because there's no magnetic fields. Of course, we have quantum mechanics issues, which is another, and I'm not sure what they're going to call photonic engineers that deal with this in the future, because you're not dealing with electrons. So it's not electronics anymore.
Right. We talked to Joe Wu, or Joe Dixon, sorry, from Wu's, who and he had made the remark in one of the earlier episodes that when are we going to get to the point where we don't have a choice, where we have to go all photonic because we reach whatever that theoretical limit is for copper on insulating dielectrics. And I think it's not too far off where the current methods that we're using for circuit board design will have to be applied to polymer waveguides or some other type of waveguide that is enabling photonics on circuit boards.
Yeah, we keep kind of running up to it, and then miraculously we invent something new, and we discover we can push the frequency door a little farther using what we've got already. Now I keep telling everybody that on a global basis, there's no race. The entire world is wired together with optical cabling. It's there. There's no thing there. I mean, everything is optical. The question mark is the last kilometer. How do you go to the individual computer or the individual office or something like that? That last kilometer, and there the horses are 3/4 around the track. The wireless method, the twisted pair method, the photonic method, and the coaxial things. And so we're still looking at that last furlong or two. For high density countries like Korea and Taiwan, they run optical cable right to the apartment building and then up to each apartment. But we're spread out over thousands of miles, and we've invested a lot of money in satellite and microwave, things like that. And so for us, it's because of our distance being so large, what's the most cost-effective way to do that last kilometer into your local neighborhood? And so, like I said, the work with Hewlett Packard was always fun because they were always state of the art, and what we called the next bench philosophy. What did the engineers need at the next bench to do their job? And this, in the test and measurement, this was pretty good philosophy, but got us into trouble in computers and networking because we had a tendency to invent to solve the problem that the engineer had, but that the market hadn't realized that yet. And so we would invent this product, and it really wouldn't sell too well because it was 3 or 4 years ahead of its time. If you look at our first portable computer, it had only a 16-line liquid crystal display and was powered by lead acid batteries, kind of thing. and it, we used it, and some OEMs and other companies used it, but until Compaq came up with kind of the modern notebook computer, notebook computers really didn't take off. The portable ones did. And even 32-bit computers, I worked on 5 separate different 32-bit computer architectural programs before HP finally settled on one. And that was because HP allowed product divisions to be competitive and autonomous. And so they would compete against, other parts of the company. And HP was the only company I ever found that had a program of recognized insubordination. In other words, HP had a corporate engineering manager who would support engineers doing private research on products not authorized by management because they didn't agree with management that the product being worked on was the right solution. And so they had to work on it on their own time, but they were essentially supported by corporate engineering. And if for some reason the product that they were working on during the day didn't mature, they would go up from under their desk and pull out to say, well, what about this? And show what they had been working on their own, which saved a day for us in many, many, many times. And that came back to the fundamental. Bill Hewlett and Dave Packard had a terrific faith in the focus of individual engineers, and because of that, they in a chain of command of executives, if you didn't have a science or engineering degree, you were relegated to the side. People with pure marketing or legal backgrounds hold only support positions. The main chain of command was always engineers and scientists, kind of thing. So after HP, I retired early from HP. I went to work for the printed circuit manufacturing company that I started for Hewlett Packard in Taiwan, in charge of their R&D, which led us to actually developing the flip chip substrate for Intel and helping Intel move into their premier position in the CPU market. And then from there to Mentor Graphics to work on the design tools for high density interconnect, because we had developed that technology in 1982, but it wasn't used by virtually anybody but us until the miniaturization of the mobile phone required that things be really miniaturized, and then high density interconnect was really the only way to accomplish that. But the design tools were woefully lacking in their ability to to optimize that technology. And then after that, my boss from Taiwan that I worked for got me involved and brought me into Foxconn, since he was the number 2 man in Foxconn. And they were having problems in their component manufacturing, which at the time, I couldn't find out any information about who Foxconn was. So he sent me this PowerPoint file with 150 slides, and I was flabbergasted to discover that they're 5 times larger than the biggest in the world, but they were all running under the radar. And then ended my career here in Michigan at a great company called Gentex here in Zeeland, Michigan, which fortunately ran a lot like Hewlett Packard. A terrific company with a lot of fringe benefits, focused on the engineer and the scientist, vertically integrated. Again, they don't outsource anything. Everything is done here in Zeeland, so they're the biggest employer in the Western Michigan. But they are highly automated. They build their own robotic automated equipment and test equipment. So it has the diversity that Hewlett Packard had in many ways, especially in innovation.
So you mentioned you went over to Foxconn and also the overseas printed circuit fabrication company that Hewlett Packard originally founded. Was this really the first time where companies were starting to push their fabrication overseas? And during that time, did they still own it? Or was this around the time where you started to see dedicated fabrication companies that were not US based, let's say, starting to come about and start to take over that market share for printed circuit board production?
Well, up to that time, we were vertically oriented. Had printed circuit operations in Scotland, in Germany, and outside of Tokyo. So we managed one of the biggest printed circuit operations in the world, but it was decentralized. I mean, there was 4 locations here in the United States that manufactured printed circuits owned by us. So we had our own kind of conference and standards and annual meetings here to talk about technology. But but what I got involved with in Taiwan was that at the time, Hewlett Packard started getting letters from countries that, Hewlett Packard is very successful in this country. We purchased $80 million worth of HP test, measurement, and computers, but Hewlett Packard doesn't buy anything from us. And so this balance of payments started getting involved. And it was implied in those letters that if HP didn't look into buying something from that country, then our products would sit in customs for 6 months or 8 months, which those countries had, could do. And so we took that threat seriously. At the same time, I didn't know this, but Taiwan, started getting in this idea that they had to diversify from sugarcane and pineapples into some high-tech product. At the time, there was an electric company in Taiwan making the displays for the IBM PC. And it was kind of clear to Taiwan that electronics was going to be the wave of the future. And so the government started this program that eventually led to TSMC. But they were also looking at, what do you do with the chips? Chips don't float. Well, they have to go on printed circuit cards. And so the Hewlett Packard management arranged a tour of Hewlett Packard's captive manufacturing in the U.S. And they came to our facility in Sunnyvale, which was highly automated with a lot of computers, focusing on the most advanced printed circuit cards that HP needed in microwave and radar and and computers, things like that. And they, the government was really impressed that this was technology that Taiwan needed. So our employees in Taiwan saw a great sales opportunity and kind of convinced the Taiwan government that, well, Hewlett-Packard would do consulting and kind of help them and pick the right printed circuit technology and the right company. And so, after negotiations, I was on a plane headed to Taiwan to spend about 12 weeks there, to spend 2 weeks with kind of the top 6 companies that the Taiwan government felt could tackle the electronic substrate problem. This was the same organization that was also courting the CMOS technology from RCA that started TSMC. So I met and worked with the people that started TSMC because I was the other half of the coin on that, under the government's tech organization called Electronic Research Service Operation, ERSO. So very much, a government-led kind of focus. And I spent 2 weeks with each of these companies and wrote a report of which one was best suited to go into the printed circuit advanced substrate manufacturing business. And it turned out to be Formosa Plastics, which had nothing to do with electronics. Now, the government was overjoyed at my conclusions because that Formosa Plastics had 6 of the most profitable corporations in the entire island making ABS plastics and all these plastic products. But delving down, Formosa did electroplating, and it did copper etching, and it had all the chemical fundamentals to making a printed circuit boards, hydraulic lamination, and all these different things. All these electrical companies, been a good job on assembly and things like that, but they didn't have any of the engineering infrastructure that it took to make a substrate. And so, they translated my report into Chinese, and the government, talked with Formosa Plastic. Formosa Plastic's board of directors was excited about the opportunity to diversify like that, especially the son of the chairman, Winston Wong, because his son actually had a PhD in material science from the UK and was very much an advocate of electronics, even though their empire was pure plastics. But with that, they said the board of directors had one thing, and it's, what's a printed circuit? And so, this American says, we have the best infrastructure, but what in the world is he talking about? And so they came back and said, well, would you write us a business plan? And after some negotiation to figure out Hewlett-Packard doesn't do this, they figured out, conjured up some kind of time and materials consulting, like we were doing on a voltmeter or something like that, thing, in order to sell my time to write a business plan for them, which was a 120-page document that I think I said 6 weeks, but it took really 8 weeks to write. It took them 3 days to translate it into Chinese. It took 3 hours for most of the board of directors to approve the project. And we were off and away, but they had one caveat. They said, well, this is a great project, but we would feel better if whoever wrote this business plan managed the project. And so HP Taiwan had the difficulty that they're going to have to convince me to take on managing this project in Taiwan if they were to sell all these Hewlett-Packard products and software. And so we did that. And unfortunately, when we started production in 1985, and the president of Hewlett-Packard was there, and ministers, and the president of Formosa Nanya Plastics, John Young turned to me and asked how much time did you take to design, do all this? We said about 18 months. And, what does it cost? I said, well, at the last running, it's about $19 million. And he said, well, I've just spent $60 million on a new printed circuit plant in Roanoke Park, California, and it's not finished yet. It'll be another 12 months. And I said, well, I know the people involved in Roanoke Park, but I've been busy here the last couple of years. And 2 weeks later, HP canceled the entire Roanoke Park printed circuit facility because this new facility in Taiwan could build the HP products. We had actually trained all the Nanya engineers actually in our manufacturing facility in California while we worked on the fundamentals of the plant. And when the entire project team moved back to Taiwan, we built up, you might say, a research and prototype facility to continue to work on chemical processes and procedures involved in the higher volume. So it was pretty clear that that this, partnership that we had created was a great way to get high quality printed circuit boards that met all of our quality standards, and knew a lot about manufacturing Hewlett Packard printed circuit boards. And that maybe there was less of a need for us to be vertically integrated and do it ourselves. So I don't know if this led to more outsourcing, but, by 2000, IBM had closed their shops and Texas Instrument had closed it. And Western Electric, and one of the things that we found out is that from 1985, for almost the next 15 years, that printed circuit facility in Nanya Plastic was the most profitable company in the entire island of Taiwan. And this would appear in the Chinese newspapers over and over again. And so I kind of believe that the Chinese reading this, that if you made printed circuit boards, it was like printing money, that, this was a really profitable things, and everybody in Asia decided to jump into it, which by 2000 and afterwards led to a kind of a collapse cost-wise of printed circuits made in North America compared to printed circuits made in Asia.
I don't want to blame HP for starting a trend, but I do see what looks like the beginning of a trend, which then culminates in the reality that you just mentioned in around the year 2000. And I think people would identify this as a critical point where the expertise that went into making that technology got exported. And, expertise is something that you can maintain locally if you have the will to do it. I think what was lost was the will to maintain that expertise and capability locally, probably for a couple of reasons. Number one, obviously there's a cost involved in that. But then number two, once you have the situation where everybody gets on board and they see printed circuit boards like printing money, as you said, and then it collapses the cost. Well, now why am I going to maintain this capability when I can just buy it for cheaper overseas? And that's how we get to that situation in year 2000. Would you say that's a fair statement?
Yeah, you're talking about globalization.
Well, sure.
And those are the error. The dilemma a lot of times was that CEOs and everybody else was working quarter to quarter based on the stock price and things like that, and so making profits became king. Whereas in Asia, I discovered that if you're going to create jobs, they would throw money at you. It wasn't profits being emphasized. No, it was jobs being emphasized. And that what they thought was a good profits, 2 to 6%, was abysmally low from a North American financial point of view. So, Hewlett-Packard had our own internal measure of profits divided by assets. And every organization in HP was ranked by profits divided by assets. And as you came to the bottom of the line, HP, took a look at, well, should we continue this business? And printed circuits was getting towards the bottom of the list because we had a lot of assets, a very complicated manufacturing process with environmental engineering equipment and things like that, and not a cheap business. And the selling price, because of Asia and things like that, was relatively low. So profits were low and assets were high. Now, the good thing about Hewlett-Packard is if they shut down an operation, they didn't fire anybody. Everybody went on what we called surplus. And the advantage of being put on the surplus list was that you could apply for any job in Hewlett-Packard anywhere, and the corporation would pay your relocation. So HP was highly diversified all over North America and Europe. But there was the condition that was local hire only. In other words, they weren't paying for relocation. But if you were surplus, you could qualify for any of these jobs. And so the people at the top of the list with high profits and lower assets needed trained people. And everybody would move from the bottom of the list to jobs at the top of the list. And at that time, as they started closing down printed circuit operations, nobody lost their job. Instead, you had the choice of quitting. You could take early retirement if you had the points and seniority, or the corporation would relocate you and everything else. And so a lot of all of my associates and engineers went into inkjet printing and the whole inkjet business, because we would take these chemicals and manufacture these inkjet cartridges for 30 cents and sell it for $35. I mean, it's like, just like HP plotter pens, which was always this thing of a couple pennies invested that you charge multiple dollars for, kind of things, is enormously profitable. And we put it into Puerto Rico where we paid no taxes, things like that. So it was, but it was always these economic conditions because, when we introduced the HP 35 calculator, marketing told us we would be lucky to sell 400 a month because they're $400. Nobody's going to pay $400 for this calculating machine. 400 a month was nothing. That was like the run of a large voltmeter or counter product. Unfortunately, within months, it went to 3,000 a day and sometimes 1,000 an hour orders. And we were geared up for 400, a month. And so all hell broke loose because everybody wanted one and we didn't have the capacity to manufacture them. So one of the things we did in 73 is our international version of our calculator was quite a bit different from the North American version because we had a language chip in it. And when you first power it up, it asks you the question, what language do you want all the error messages and everything else? And once you tell it, then that's sealed in. That calculator will speak that language to you. And so Singapore offered us a tax-free status if we would build those calculators in Singapore. But it had to have over 25% Singaporean content. Well, Singapore, all it had was low-cost labor. It didn't have any of the semiconductors or anything else. And we couldn't get to 25%. But we did make the calculation. If we made the printed circuit card in Singapore and then assembled it, it would be 27%. And so my group got the job of building a printed circuit factory, designing a printed circuit factory in Singapore there first. But we wouldn't run it. What we would do is we would find a partner there in Silicon Valley that wanted to be international. and we would provide the design and the money to build the factory, but they would actually own it, and that was the first printed circuit fabrication multilayers in Singapore. And unfortunately, that model worked so well that over the next 20 years, every time we got hit with a country saying, you're not buying anything from us, the board of directors turned around and said, well, let's send Holden over there to build a printed circuit factory, to appease them. With the success of the Formosa Nanya project, we knew how to do that. And it was like our low-hanging fruit, teaching them to make the semiconductors and all the other parts of the calculators, LED displays wasn't going to be something that we can manage. But circuit board manufacturing was something that we could teach and manage in a reasonable time.
This is really interesting because, there's this narrative that, globalization was just driven by companies, profit seeking, and that's kind of the end of the story. And I'm hearing so many different dynamics here, right? You have government support from those overseas countries, and in some cases mandates, like you just brought up, to have the manufacturing there in the first place in order to do business. And so the government is on the other side is creating the situation as well. And I understand that in the, American financial markets, there is kind of this focus on productivity and what the profit margin is and these other metrics that drive stock price. And of course, there's executive compensation that's tied to stock and these types of things that create those incentives. So I'm not saying that, profit isn't part of that. But given that there is a trend towards onshoring now in the printed circuit industry and the electronics industry more broadly, it almost seems to me that the American side of the electronics industry might have to copy some of those focuses and policies from overseas in order to bring that manufacturing back, or at least diversify it a little more geographically, so that we don't have some of the supply chain problems that we've had in recent years. And I think you brought up one point, which was the focus on creating more jobs by some of these overseas companies and by the government, where the jobs was the measure of profitability and not necessarily the profit margin. It would be interesting to see that happen again here and have companies be financially rewarded in some way for job creation and not necessarily for, let's say, having a higher profit margin. What do you think about that?
Well, yeah, it's very clear to me that, the government was very much focused on a 20-year program of how to bring advanced jobs that were higher paying and required a higher skill to Taiwan was a government imperative. Now, they selected electronics. The dilemma that we have here in North America is we keep inventing so many different markets that the government is hard pressed to pick one winner. You really can't. Well, should it be the electric vehicle? Should it be electronics? Should it be pharmaceuticals? Should it be military products? Should it? We've got just everything under the sun here. In Asia, they pretty much all selected electronics, and I don't know what genius kind of convinced them of that. It's probably another American consultant convinced them of that kind of thing. But the second thing is that they looked at it from a 20-year point of view. In other words, we knew that starting up a printed circuit manufacturing operation, you've got a lot of training and a lot of process improvement and yield improvements. And so I don't know if the government subsidized so much, but I'm pretty sure that the government provided Formosa with 5 years in which the government guaranteed they wouldn't lose money. In other words, it wasn't a flat out, subsidy or anything like that. It was just that,
It was like it was backstop.
yeah, it was the thing is that we won't let you fail, or we won't let you, lose and go bankrupt in this. But you've also got to, to keep working on it. And so one of my partners at Hewlett Packard, Dr. Clinton Chow, a really enormous, brilliant scientist from HP Laboratories, and, big in semiconductor packaging. When he retired from Hewlett Packard, the Taiwanese swarmed all over him. And he spent the next 5 years at TSMC inventing all of these processes that they're talking about now. That wasn't done by the Taiwanese. That was done by Dr. Chow and his team from Hewlett Packard. And he was working with the other scientists retired from IBM, and the other scientists retired from Texas Instruments. Again, this American cadre providing that technology with unlimited funding to do that. And so
it's almost like we shouldn't be surprised that the knowledge has just been kind of sucked out, at least in terms of advanced fabrication capabilities. It's almost been sucked out to the point where there's just no one left to maintain that, and we almost have to relearn a lot of this as it develops from overseas. If you're recruiting all of the best people who have retired and having them come work for you in Taiwan or some other country, yeah, of course you're going to get some of the most advanced processing capabilities very quickly, especially if you just throw money at the problem until it works.
Right, and so it's taken us 30 years to lose this edge that we had. And so when I look at the CHIPS Act, that $52 billion is only a down payment. The problem's not going to be solved with that one payment. That's just the down payment. If we want to gain back that 30 years that we lost in something like 5 or 10 years.
But I think that money is more meant to say, or to show a willingness on some level to provide that support, because that seems to have spurred off other investments from other companies. And when you add up some of those dollar figures from Intel, from Micron, from Samsung, from Global Foundries, and you go down the list, like, it's a significant amount of money. It's like a U.S. defense budget, a significant fraction of that amount of money that's being invested in capacity here in the U.S., and some of it in the most advanced nodes. So I understand what you're saying, that yes, $52 billion is a down payment. And I agree with you. I think it is just a down payment for now. But I'm thinking it's also a step in the right direction, in that it does spur private investment, which I think was the intent.
Yeah. And fortunately, they're putting together research and other organizations to talk about the entire supply chain that has to come to North America, not just the chips, but, we've got to have advanced flip chip type substrates for them to go on. And we've got to have the OSATs that do the assembly and testing. And that we currently have the prototype capability of that technology in North America, but not the volume technology. All the volume is in Asia. And so I expect that out of the CHIPS Acts and other investments, we'll have capability of medium volume semiconductor products. The high volume stuff is still going to go to Asia, because from a North America point of view, our biggest TTM, is already building a $5 billion facility in Malaysia for advanced PC boards. And the biggest in Europe, AT&S, is also building an advanced PCB facility in Malaysia, Penang. In terms of the high volume stuff, it's still going to go back to Asia, but it's not going to go to China. Everybody is figuring out how to leave China as quickly as possible. the various things. And so, our CHIP Act just kind of helps the movement both of onshoring, but also alternative to China offshoring that's safer. I've spent a lot of time in Malaysia. Hewlett Packard has a huge Malaysian assembly plant for semiconductors, and it goes all the way back to the early 80s, especially in Penang. So that's a logical place to build it. But we've got to be more critical of our supply lines for critical components and products used in aerospace, military, or pharmaceuticals and things like that. We can't have these key areas without a supply loop, a supply chain that we can depend on if times get troubled, kind of thing. Now,
so one of the relating to that, sorry to interrupt, but relating to that, one of the things you mentioned earlier, which I was a little surprised by, was that Texas Instruments did their own PCB fabrication and assembly, and there were other companies I think that you mentioned that also, everybody did it.
I mean, it was called captive. There's only 5% was a merchant market, very, very small. But
do you think it'll ever go back to that? I mean, because we already see some things with semiconductor design coming in house at like Tesla and Apple, and so I'm wondering if there are other aspects of product, not just product build or product design, but product manufacturing that are going to come back in house, where companies are going to own more of that capacity rather than waiting for the manufacturers to bring capacity back, to bring in for like Intel to bring capacity back, or for Global Foundries to bring capacity locally. Do you expect some of those companies to maybe invest more in their own production rather than doing these kinds of partnerships or hoping another manufacturer will do it for them?
Well, I certainly hope so. I mean, when I started, the OEMs, my peers were at IBM and Texas Instruments and Western Electric, and other OEMs. My peers were not a small bucket shop making prototypes or something that was poorly capitalized. No, it was the big OEMs, and the fact that we all got out of it so fast, left an enormous hole, because what we would do is we would innovate technology constantly at HP, inventing and developing new things. And we would put that into our own factories, but we still had to make the older printed circuit boards. And so we would push that out into the merchants. So, we had a pipeline of technology driven by these products. Today, we don't have that pipeline because OEMs know nothing about researching a printed circuit board. But at Hewlett Packard, when we came up with a new product and formed a team, the team was the component manufacturing in Hewlett Packard, the assembly part of Hewlett Packard, and the electrical engineers and design and the semiconductor. We would meet at this team, and we would do a round robin of innovations in terms of what they wanted to achieve that was better than anybody else. But then we'd start talking about the problems. And one person would say, well, I can do this, but I had this problem. And then another part of the team is, well, wait a minute, we can solve that problem for you, but it all then creates this problem. And we would kind of share, so that everybody shared in innovations that seemingly were a far stretch. But as a team, and then the company would finance the whole thing, and we'd all go off with aggressive schedules and work like hell and then pull it off. And so, like the HDI technology that we developed in 1982, we did that because we had this world's first 32-bit microprocessor on one chip, a complete 32-bit computer. It's done with NMOS 3, which is very high current, but very fast technology. And when we mounted that thing up on the packaging and put it on a printed circuit board, it didn't work. And it didn't work, we found out, not because there's anything wrong with the chip. The chip could not drive the inductance of a through hole, could not, and did not have the amount of energy required to handle FR4, epoxy glass laminate. So the scientists were back calculated, and they said, all right, we have to have a printed circuit board with the inductance of the hole. Can't be any more than this picohenries. Consequently, it can't be any larger than 5 mils in diameter and 5 mils deep. And in order to get across the circuit board energy-wise, our NMOS3, instead of 0.08 dielectric constant, we had to have a material that was 0.0002, which was pure Teflon.
Right.
And so they came to us and said, we need a printed circuit board. The vias don't go all the way through the board, 62,000. No, they can only go 5 mils deep, and they only be 5 mils in diameters. Right now, we're drilling 25 mil holes, 60,000 through the board. And so we had to go out and invent and create a laser drill. We had to create plasma etching in order to make things stick to Teflon. And then we had to develop the selective copper nickel pure gold plating for wire bonding. And lo and behold, this thing had the heat dissipation of a nuclear reactor. So we had to make the core of the printed circuit metal and create a cavity, put the chip down on the metal to keep the thing from burning itself up. And so the HDI technology came about not because of density, but because the chip technology demanded that from it. And over again, it's been the semiconductor technology that drives the electronics industry and everything that happens in terms of rise time. But because of our unique chip, nobody else weren't interested in the technology, because that was a chip that we designed and we made unique to us. Now, we got into a lot of trouble with the government because the government told us, we don't mind if you make 32-bit computers if they're the size of faxes. They weigh 1,000 kilos and are a 19-inch rack. But yours is smaller than a kid's lunch pail, uses silicon on sapphire, which is radiation hardened, is not air-cooled but conductive cooled, and hermetically sealed. And so we've spent over $600 million in the Department of Defense trying to develop warhead computers. And you're going to introduce the damn thing for $5,000 ready to go, so you have to cease and desist. You cannot sell these computers because they're militarily too advanced, more advanced than anything the U.S. government has, because we didn't tell them that we were inventing this computer. Now, fortunately, we came to a compromise because David Packard was in the Defense Department at the time. And the compromise is that we would serialize every single PC board that we made for this computer, and we would visit it every 6 months to make sure it hadn't been stolen by the Soviets, because it was years and years ahead of anything the military thought about and even had, just because of the evolution of semiconductor technology. But until everybody else got need of miniaturization or the electrical performance, the HDI technology didn't really take off until later, 1997, when we redesigned the Motorola MicroTac from the crazy thing Motorola had put together into an HDI version that we could do, because we said, your R&D guys came up with a great product here, but a 7-layer PC board of non-uniform cross-sectional area is going to fold up like a potato chip. And we don't have any magic to make this thing, but we could redesign it for you so that it could be manufactured, kind of thing. But the age of miniaturization started with those handheld calculators. We started making things to fit in your hand, and things haven't changed since then, except that we're going faster and faster into this. And no matter what you do with the chips, there still has to be mounted on something to bring it out to the real life and everything else. And that's the printed circuit board. We change chemicals, processes, materials, but it's still a substrate of some sort.
Sure. Well, I know we're getting up there on time. This has been such an enlightening conversation, though, and hopefully soon we can have you back to talk more about some of these points you just brought up as far as HDI and then the packaging, because they're so closely related. And I think even if you look at the cross section of packages and substrates, they start to look a lot like HDI printed circuit boards. So I think it's very relevant for designers today, especially as some of the designs that people have to do get more and more advanced.
Yeah, and in the IPC, our committee calls it Ultra HDI.
Right. Yes.
And we're calling Ultra HDI to differentiate from advanced IC packaging, which is always going to be the leading edge. But what happens if it's a larger board, not the size of a package that's 1 inch by 1 inch or 2 inch by 2 inch? What if you want 6 by 8 inches? But
sure.
you want semiconductor-like features. Well, we kind of label that an Ultra HDI. But yeah, electronics is always going to be highly diversified, and it's going to go in all these directions, which is why I tell students that we lecture to that if you're picking electronics, you pick the right profession, because it'll keep you busy for the next 50 years and should provide a good living, but provided you're willing to constantly be re-educated, because you just can't go to college and then expect that's all you'll ever need. You're going to have to constantly up your education continually, because we keep changing the nature of chips and how they're built and what they perform. I mean, I'm still struggling to understand quantum computing. I mean, I'm used to, ones and zeros and bits and bytes, and the whole quantum stuff, it's kind of taxing on my brain.
Well, I think that's a great takeaway message for listeners. Don't stop learning. And that's what we often say here at the end of these episodes. So first, I want to thank you so much for joining us. And second, to anyone that's out there listening, if you want those resources to continue learning and investing in your professional education, of course, hit the subscribe button on the Altium Academy YouTube channel. As all of our podcast episodes and tutorials come out, you'll be able to keep up with those. And we'll keep pushing out this great content so you can make sure you maintain your edge in the electronics industry. Happy, thank you so much for joining us. I'm going to happily have you back here on the podcast again so we can talk about some of these other issues that you brought up, because this is so enlightening. And I think so many people need to learn this history so that they can see where things are going to go next in the industry.
Well, glad to help out. Because fortunately being retired, I've got the time to think about that and lecture and also write books, which, like I said, they can go to the iConnect 007, which is the IPC publishing group now. There's 24 to 26 free electronic books on this, including 3 books that I've written about automation and processes and HDI that are available for you, free of charge. Download it, but they're electronic. Don't necessarily advocate printing them, since you can store everything you want in a modern smartphone or tablet. You can carry your whole library around with you.
Absolutely. And we will link to that in the show notes too, for anybody that's listening, so folks can click over to that and access that material.
Yeah, because like you said, there's a need for continuous education and learning in this profession. It's not one to sit back and rest on your laurels.
Absolutely. Well, thanks again.
I'm glad to talk on any subject you kind of come up with, whether or not I have an expertise or not.
Sure, definitely. We'll do it again. Thanks again to everybody that's listening. Like I said earlier, make sure to subscribe, make sure to hit that like button. We always like getting your comments and questions. And of course, don't stop learning. stay on track, and we'll see you next time.